Okay, we're back with the third part of our series of lectures here on arithmetic sequences. So if you recall, in the last two parts we looked at a couple of real-world examples where we were doing some physical arrangements. Task 1 was dealing with arranging seats for a band. Task 2 was arranging a set of blocks. And Task 2, of course, was basically the same idea as what we had on our Minds On project that introduced this, at least the arithmetic sequence part of that project. So in this video we're going to continue this by doing some problem solving exercises and applications. So first we're going to do a series of exercises showing how we can start with any one of the given forms and produce some of the other forms. So how we can use the structure we know about the recursive form to find the non-recursive form, the graph, the table, and so forth. And we'll see how to get from any one of these representations to the others. So the first exercise, we're given a recursive formula. So in this case, the recursive formula we're given is a1 equals 6 and ak equals a sub k minus 1 minus 4. So how do we know this is an arithmetic sequence? From this, how can we tell just by looking at this as arithmetic? Then list the first 20 outputs, give me the slope-intercept, y-intercept form of the equation, give me the point-slope form of the formula centered at the input at 5, give me a table of the first 12 points, and give me a graph. So you should be able to do this at this point. Go ahead and do this now, and then come back and check it with the video in just a minute when you finish. Press pause now. Well, hopefully you've tried this and you found that we know that this is an arithmetic sequence because we can get from one term to the next by adding the same amount each time. In this case we're adding -4 each time to get from one term to the next. So that makes it arithmetic. So the first term is 6. Technically there is no 0th term here. This particular one starts with 6. Sometimes we start with a 0th term. Sometimes we start with a first term. So here the first term is numbered 1 and its output is 6. So 6 is our first term. We subtract 4 from that, or add -4 to get the second term, which is 2. Add -4 to that to get -2 for the next term. Add another -4 to get -6, and so forth. And you see there the first 20 terms. Oftentimes sequences are given like this as just an ordered list. We can also develop an explicit formula. We've seen that the form in general for an arithmetic sequence is a sub k equals mk plus a sub 0. So m is the common difference or slope or delta y. It's what we add to y each time when delta x is 1, or when we add 1 to the term number. So in other words, as we go one further in our terms, one further in this ordered list, we're adding -4 each time. That's the m, the slope, and that's the coefficient here. So it's a sub k equals -4k plus a sub 0. Well, a sub 0 is the 0th term. Well, technically this one doesn't even have a 0th term, but you can figure out what it would be by extending the formula, extending the pattern back. So notice as we go to the right one in this sequence here, we're adding, of course, we're adding one of the term number, but we're adding -4 here. So if we go the other way, we subtract the -4, in other words, add 4. Add 4 that then. So we're subtracting 4 going when we increase the term number 1, increase the term 1. When we decrease the term 1, we add 4. So add 4 to 6, we get 10 is the initial, the 0th term if there were one. And so we get a sub k equals -4k plus 10. And of course you can check out to make sure that works. Plug in k is 1 and you do get 6, k is 2, and you do get 2, and so forth. So here's our same thing in table form down here where you have the first 12 things, and then here's the graph over here in a regular Cartesian coordinate graph. Notice the first dot occurs at 1, 6, then we have 1 at 2, 2, and at 3, -2, and 4, -6, and so forth. These dots continue down and to the right forever, but the first dot actually is 1, 6. There's nothing before it. The point slope formula is centered at 5. In general, a point-slope formula looks like a sub k equals m, parentheses k minus a something, minus the, well, let me say it this way. A sub k equals m, k minus some particular k, plus the particular a sub k. Okay? So, the particular input we want is 5. So it's negative 4, parentheses k minus the input, so that's k minus 5. And then you have plus the output. Well, the output on the fifth term, you can look in the table or just count out in our sequence here or just work it out, and it is negative 10. So the formula is negative 4 times k minus 5 in parentheses, and then minus 10. So we could start with the recursive form and get the other versions. Suppose we start with the slope y-intercept formula. A sub k equals negative k plus 100. How do we know it's an arithmetic sequence? Find the other forms for me. Go ahead and do this now and then come back. Press pause now. Well, we see this is one of the correct structures. Output equals a constant times input plus another constant. That is exactly the slope-intercept formula, slope y-intercept formula for a sequence like this, for an arithmetic sequence. And so we could work out the formula if you plug in. This one actually starts with let's say it starts with the k equals 0. So 0, you plug in, so a sub 0 equals, the opposite of 0 plus 100 is 100. So 0, 100 is your first term. Then you plug in 1, you get negative 1 plus 100 is 99. You plug in 2, that's negative 2 plus 100 is 98, and so forth. And so we see that what we're doing is we're just going down 1 each time, starting with the 0th term of 100. So recursive formula is a sub 0 equals 100, and a sub k is a sub k minus 1, and then subtract 1 from that. And of course that second formula works for all the k's that are natural numbers. If we center it up at 5, we get a sub k equals m, which is negative 1, parentheses k minus the input, specific input of 5, and then plus the specific output that goes with 5. The output that goes with 5 is 95. And then we have a graph. Now, this is really not too good. If I really had this graph, if I'm going to show this much of the window, I should show the dots going all the way off till they leave the screen. But I just have some of them graphed here. So here we have this graph. There is a point to the left, which is the first point, 0, or the 0th point. It's the furthest one to the left, 0, 100. Then you have 199, 298, and so forth. But they do actually go forever to the right and down. What if we're given a point-slope formula? How do we know that's an arithmetic sequence, and then figure out the other stuff? Okay, the other forms, other representations. So we have a sub k equals 3.5 times k minus 4 plus 0.5. See if you can work this one out and come back. Press pause now. So what we see here is that this is an arithmetic sequence because it's the right form. It's a sub k is a constant times parentheses k minus another constant in parentheses plus another constant. That's exactly one of the forms that we know that works, and we know what those numbers mean. We know that this is centered up at the point 4, comma 0.5. So the fourth term is 4, comma 0.5. That's one of our points in our table or in our graph. That table is completely messed up, and so is the graph. Okay, tell you what, we're going to fix that. So that table is just messed up. I can fix it from here. So if I want to fix it from here, I need to do a little bit of more work. So let's go back here. See if the rest of this is right. So we know that the first term we could get by plugging in 1. 1 minus 4 is negative 3. Negative 3 times 5, negative 10.5 plus 0.5 is negative 10. So that's good. It does start with negative 10. And we're adding the 3.5 each time. So that's a correct recursive formula. The non-recursive formula is 3.5k plus a sub 0. And so we'd have to go one term further back than actually exists to the 0th term. You could actually do it by plugging in the formula above, plugging in 0, or just going back an additional 3.5 and you get negative 13.5. Okay, so the way this sketch is over here, I need to start with the 0th term, which is negative 13.5, and I want to go up by, what was it? 3.5. And there is our table. Okay, so there's our table of our first ones. So let's go ahead and put that down here. So we'll get that fixed up. Okay, now hopefully that is not only correct, but it agrees with what we have up here in the table. Well, it would if I would get the rounding right. I've got this set up. Problem is these are not rounded off right. Okay, you know what? I'm going to fix this. I'm going to fix this later. Okay, so let me go ahead and get a graph of it though, which I could do now. This includes a 0th term, which we will not include. Whoa. And we'll look at this here. And this is a correct graph. Okay, I'll fix the table in a little bit, and then we'll come back to that. Okay, so let's continue on. So I'll fix the table for the slides that you'll have to print out. But of course, you know what it is. These are the outputs right here, and the inputs are just 1, 2, 3, 4, 5, 6, 7, 8, 9, and so forth. Okay, here's one. Perhaps this one relates to a blocks example again, where we have this, and we have our step number and our number of blocks. And this one we have a table. How do we know this is arithmetic and get the other representations? Go ahead and do this one now. Press pause. Well, here we see that the inputs are natural numbers, or actually are whole numbers. So it's a sequence. And the outputs are going up, so they're going up by 1s on the inputs. The outputs are going up by 2 every time, so that makes it arithmetic. You have to check all the way up and down this table to make sure that's true all the way. But since delta y is 2 every time, that is the slope, because delta x is 1, and so that's a constant. And of course we can continue that on past the 32 here, 34, 36, and so forth. The recursive formula is we start with the 0th term of a equals 8, and then we get a sub k is a sub k minus 1 plus 2, because we're adding 2 each time to the previous term. The slope y-intercept formula is a sub k equals 2k plus 8. Remember, this 2 is the slope, how much we're adding each time, and the 8 is the 0th term, which you can read right there off the table. If we want to center it at 5, we just need to find a 0.5 here for input, so we see the 0.518. So it's a sub k equals 2 times k minus 5 plus 18. Remember, the 5 is the input, the 18 is the output that goes with that, the 2 is the slope. It would also be, for example, we could center it up another point. We could say a sub k equals 2 times k minus 10 plus 28. That would work. We can center it up at any one. And here's a graph. This one does have a 0th term. And notice every time we go to the right one, we're going up 2. Okay, so we're going right 1 and up 2 every time, and that's what makes this thing straight. Okay, so here we have a graph of a sequence. Can we make, first of all, how do you know it's arithmetic? And then see if we can find the other representations. Go ahead and do this one on your own if you can. Press pause now. Well, let's see. The fact that these are dots in a straight line, that's going to make it an arithmetic sequence. And of course, there's a dot for input or x or whatever of 1, 2, 3, 4, 5, 6, 7, 8. So this is a sequence starting at 1. These yellow dots aren't part of the graph. They're control points. And we see that these dots are all in a straight line, so it actually is arithmetic. Okay? And so reading off the graph, we can see the outputs are 17, 16, 15, 14, 13, and so forth. And there we have it. So what we're actually doing is going down 1 as we go to the right one. So the recursive formula is you start with A1 is 17, and then A sub k is A sub k minus 1 minus 1 more. So A sub k is the opposite of k plus 17. That's not right. That should say we need to, this one starts with a first term of 17. That needs to be the 0th term. So let me fix that. Okay, this should say we need to figure out what the 0th term would be. So if we went back one more, that would be actually 18. So we can fix that. Okay, now there we go. That looks better. And so now if we were to continue this back to a y-intercept, it would hit at 18. And that should still agree with it. So when you put in k as 1, you get 17, k as 2 is 16. So there's your table down here. And if we want to input at 8, we have 8, 10 as our ordered pair. So it's k minus 8 plus 10, but then we have our slope in the front here, a negative 1 there. Alright, here are some sequences listed out as just ordered lists. Some of these may be arithmetic and some may not be. Tell me which ones are arithmetic and how you know. And if it is arithmetic, give the next 3 terms, the slope y-intercept form of the equation, and then figure out the 100th term. If it's not arithmetic, tell me why you know it's not arithmetic. And if you can, go ahead and figure out a formula for it, but it's not going to be an arithmetic kind of formula. See if you can work on these now. Press pause, come back when you're done. Well, the first one does have a common difference of 5. 2 plus 5 is 7, 7 plus 5 is 12, 12 plus 5 is 17, 17 plus 5 is 22, 22 plus 5 is 27. So we're adding the same amount each time. Of course, you find that by subtracting. 7 minus 2 to get to 5. 12 minus 7 is 5. 17 minus 12 is 5, and so forth. So since this has a common difference of 5, that is the slope, we can continue to add 5 each time to get the next 3 terms, 32, 37, and 42. This is an arithmetic sequence, and so a sub k equals mk plus a sub 0. The following sequences start with term 0, so that's common difference is 5. The initial term is 2, so a sub k is 5k plus 2. And if we want to do the 100th term, plug in k equals 100. So that's 5 times 100 plus 2 is 502. The next one is also arithmetic. When you do this common difference here, it's negative 3. 50 minus 53 is negative 3. 47 minus 50 is negative 3. 44 minus 47 is negative 3. 41 minus 44 is negative 3. So what we're doing is we're adding a negative 3 each time, or subtracting 3 each time as we go to the right. So if we continue to subtract 3 each time, 41 minus 3 is 38. 38 minus 3 is 35. 35 minus 3 is 32. And so we have the next 3 terms. The formula is a sub k equals negative 3k plus 53. Remember again, it's our basic form of a sub k equals mk plus a sub 0. A sub 100, we plug it in, and that one, obviously I did a little copy and paste and didn't fix it here. This should be negative 3 times 100 plus 53. So that's negative 300 plus 53. is negative 247, I believe. Let's see. Yes. Okay. Let's go back. Okay, that looks good. Alright, the next three, none of these are arithmetic. They don't have a comma difference. So let's check it out. When we try to find the comma difference find the differences on the third one, we get negative 4 minus 2 is negative 6. Then we get 6 minus the negative 4 is 10. And negative 8 minus 6 is negative 14. So those are not the same. So this is not a comma difference. Okay, but this one's kind of interesting though. If you would ignore the signs and just did the absolute values, you do get a comma difference. You get it going up by 2. So the absolute values of this are actually arithmetic, but then it alternates signs. So we can continue this pattern. It's not an arithmetic sequence, but it is like an arithmetic sequence but with alternating sign. So the next one would be positive 10, then negative 12, then positive 14, and so forth. And of course, if you just did the absolute value, we could use our arithmetic formula. A sub k is 2k plus 2, but then the alternating sign we can get by putting negative 1 to the k power. Notice when k is an even number, negative 1 to an even number is 1, positive 1, so we get a positive term. On the even terms, like the 0th term, the 2, the second term, the 6, the fourth term, the 10. And then the odd numbered terms, when we have negative 1 to an odd number, that becomes negative 1, so the whole thing is negative. So the odd terms will be like the first term, negative 4, and the third term, negative 8. Notice the first one that's actually listed is really the 0th term, the way we're labeling these. So we can figure out the 100th term. The 100th term being an even term will be positive. And 2 times 100 plus 2 is 202. So that one is 202, positive. The next one, 13531, this does not have a comma difference. The differences are 2, 2, negative 2, negative 2. So this is not arithmetic. Don't know what this pattern could be. It might be a number of different things. For example, it could be 13531, 1357531, 135797531, etc. You could do something like that. But that's not the only pattern it could be. There are many, many different patterns that you can use. And in fact, on these that are arithmetic, as a possibility, that's not the only possibility. So there are other patterns that these things could be, but right now we're just seeing which ones could be arithmetic. The next one, when you look at the common differences, or not the differences, they're not common. The differences on the last one there are 2, 4, 8, and 16. It actually turns out that this doesn't have a common difference, it has a common ratio. 4 divided by 2 is 2, 8 divided by 4 is 2, 16 divided by 8 is 2. So this is actually what's called a geometric sequence. So instead of adding 2 each time, we're multiplying by 2 each time. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. Now we can continue. 32 times 2 is 64. 64 times 2 is 128. 128 times 2 is 256. And so these actually turn out to be powers of 2. Since I'm starting with the 0th term, I need to put k plus 1 for my power. So notice if I plug in 0, I get 0 plus 1 is 1. 2 to the first is 2. I plug in k is 1, I get 1 plus 1 is 2 for the power, so 2 to the second is 4. Plug in 2, 2 plus 1 is 3, 2 to the third power is 8, and so forth. So if I want to do the 100th term, it would be 2 to the 101 power. Okay, which is a really, it's got 30 digits in it. I'm not going to write out all 30 digits, but it's approximately 2.53 times 10 to the 30th power. Alright, now let's do some real-world applications. Suppose that you currently have a collection of 259 magazines and that you have subscriptions for 6 magazines per month that you will add to your collection. Write a recursive formula for the number of magazines in your collection, N. Write a non-recursive formula for the number of magazines in your collection, N, as a function of the number of months from now, little m. And how many magazines will you have 1 year from now? Actually, that's a poor choice for little m since I've been using that for the slope. I think I decided to change it to k. Okay, so here's what we turn out to be. Whoops, I should have had you do that. Here, press pause and do it yourself, and then come back and check it. Okay. Now we're back. We notice that the recursive formula is n sub 0 is 259. So 0 months from now, we have what we have now, which is 259. And when we're k months from now, we'll have n sub k, which is n sub k minus 1 plus 6. So at any month, we'll have 6 more than we had the previous month. So that's a recursive formula. A non-recursive formula would be n sub k equals the slope, how many we're adding each month, which is 6, times k plus our initial amount of 259, the 0th term. So n sub k equals 6k plus 259. So how many will we have 1 year from now? Well, 1 year from now, 12 months would have passed. So we'll have, that will be n sub 12 is the number we're looking for. So 6 times 12 plus 259. 6 times 12 is 72. 72 plus 259 is 331. So 1 year from now, you will have 331 magazines in your collection. Alright, here's another application. For several years in a row, the number of students enrolled in a university is given as a function of the year by the formula n sub y equals 110, parentheses, y minus 2,000 plus 6,987. What kind of function is this, and how do you know? And what do these numbers have to do with anything? What's the 110? What's the 2007? What's the 6,987? So note this is a point slope form. What ordered pair is this centered on? And interpret the meaning of that point. And then figure out how many students were enrolled in 2011. Go ahead and do this one now. Well, this is the form of an equation for an arithmetic sequence. Of course, that's a linear function whose domain is part of the natural numbers. So the actual domain for this problem is the several years in a row. It's those particular year numbers. Presumably the several years, maybe they start at 2007 or near 2007, and there would be a few years. This formula wouldn't necessarily work for all years, but it will work for some nearby. So this formula is in point slope form, and the ordered pair that it's centered on is 2007, 6,987. So you can check out that that point does work. And so what this means is the input is the year number, the output is enrollment. So in the year 2007, the enrollment of this university that we're talking about was 6,987. So how many students were enrolled in 2011? Well, that would be n of 2011. Notice I've used function notation here instead of sequence notation. Doesn't really matter. It's still the same thing. You've got an input of 2011, and we're trying to find an output for that goes with that. So whether we call that n of 2011 or n sub 2011, it's the same thing. It's the n that goes with an output, the output n that goes with an input of 2011. So anyway, just plug in 2011. 2011 minus 2007 is 4. 4 times 110 is 440. 440 plus 6,987 is 7,427. Okay, so in 2011 there were 7,427 students enrolled. Really, if you're going to ask a question in terms of a real-world scenario, you really should enter your answer as a sentence. Okay, let's try another application. The cost of selling t-shirts for a fundraiser as a function of the number of t-shirts purchased is C of n equals 5.25n plus 37.50. Explain the meaning of each part of the formula in the context of the problem, and be sure you include appropriate units in your explanations. How much is the supplier's setup fee, and how much will it cost to produce 50 t-shirts? Okay, go ahead and see if you can answer this and then come back. Press pause now. Well, the N is the input, which is the number of t-shirts purchased. C of N, or just C, is the total cost of purchasing the N t-shirts. 5.25 is the unit variable cost, and that would be in dollars per t-shirt. Okay, this is above this. It's above the setup fee. This is sometimes known as the marginal cost, and it's the cost of each additional t-shirt ordered above what you had previously. So when you multiply that by the number of shirts, the 5.25 times N, okay, that's dollars per shirt times shirts is dollars. That is the variable cost. But then we also have this constant term, 37.5. That's $37.50, which is our fixed cost, and that's the supplier's setup fee. Okay, so in other words, the supplier is going to charge you $37.50 to set. Maybe you're printing a silk screen on t-shirts here, for example. So to set up the machine to do the silk screen, he's going to charge you $37.50. If he sets that up and then you don't buy any shirts, he's still going to charge you the $37.50 for setting that up. Okay? Now whether you make one shirt or 100 shirts, that $37.50 is a flat rate. Okay? But then you also have the $5.25 per shirt, so that's the cost of ordering the shirt itself. And then that you add all this together, that's going to be your total cost. So for example, to do 50 shirts, it'll be $5.25 times 50 plus 37.5. That turns out to be $300, so it will cost $300 to buy 50 shirts. So for just to do a little part of the table here, if you do 0 shirts, it's $37.50. 1 shirt would be $37.50 plus $5.25. That's what would that be? $42.75. And then another $5.25 for the next shirt, and so forth. Alright, application 4. A new employee signs a 10-year contract with a starting salary of $50,000. His contract guarantees a raise of $300 per year. Write an explicit formula giving his annual salary S as a function of the year's work, T. Let T equals 1 correspond to the first year's salary. How do we know that this relation is an arithmetic sequence? What is the value of the slope for this function? And be sure to include appropriate units and give an interpretation of the slope in the context of the application. And what is the salary in the 10th year of his contract? See if you can work this out and come back when you got it worked out. Press pause now. Well, we can do the explicit formula in a couple of different versions, in a point-slope form or a slope-intercept form. Since we know the point, t equals 1, then s is 50,000, we could use a point-slope formula, and we know the slope is 300 because that's how much it's going up. The salary is going up each year. That's what a raise means, is how much you're going up. So s of t equals 300 times t minus 1 plus 50,000. Or if we just distribute and combine like terms there, or just go backwards 1 in our table to a 0th term, we could put it in the slope y-intercept form of s of t equals 300t plus 49,700. So those are, either one of those would be a good way to look at it. The fact that it's linear or arithmetic is because it has a constant slope, in other words, a constant rate of change. In other words, every year we're adding 300 to the salary, so that makes it arithmetic. What's the value of the slope? Well, that's $300 per year. Notice that it is dollars per year. And the amount the salary goes up each year is what that represents, so that's the annual raise. It's the rate of change. What is the salary in the 10th year? I used the slope-intercept form and plugged in 10, but you could plug in 10 in the other version either way. And let's see, 300 times 10 is 3,000 plus 49,700 is 52,700. So the salary in the 10th year is $52,700. By the way, on this previous problem back here, it never really said what our units were for the money, right? I mean, it could have been euros or yen or pesos or something, but we're in the United States, so if we don't say otherwise, we'll assume that we're using American money, so it'll be dollars. If we're going to use some other currency, we'll need to specify that. In this problem, dollars were specified. Okay, so we've seen in this video some applications, real-world applications. We've seen some problems where we just exercises where we manipulated different forms around from one form to another. So what are some of the goals and objectives when we put these three videos together on arithmetic sequences? Well, with or without the aid of technology, you should be able to, for arithmetic sequences, describe the structure of the table, the diagraph, Cartesian graph, and formula, and the formula in recursive form, slope y-intercept form, or point-slope form of these arithmetic sequences. And you should be able to determine if a relation is an arithmetic sequence given any of the forms above, and find the representations above given any one of the representations. In other words, if you start with any one of these, you should be able to get all of them. And you should understand all of the parts and the structures of each of these representations. What structure you see in the formula, what structure you see in the graph, and so forth. And you should be able to apply these concepts to real-world applications and use them in doing some problem solving. Linear functions, including arithmetic sequences, are the most important class of functions. They're also the easiest class. I mean, I guess constant functions really are the easiest, but even then, constant functions really are lines, so they're actually a subset there of linear functions. So they have one of the easiest graphs, straight lines. They have one of the easiest kinds of structures in the formula, and they're also very useful in real-world situations because many real-world situations can be modeled by linear functions or arithmetic sequences, and even functions that are not really linear over the long period of time may be approximately linear even if you look at a short period of time. So this is a very important class of functions, and we need to learn how to really work with these very well, and we'll continue this in our next section as we take this same idea but now extend our domain to where we have not just natural numbers or whole numbers for inputs, but also any real number for an input, and so now our graph becomes a solid line. And we'll be looking at that in our next unit, or next section of this unit.